Hello Science 30s. I'm going to do a video on the universal wave equation. And so the universal wave equation you will find on page 3 of your data booklet. And the equation is written in two different ways. It's either going to be written as v equals f lambda or c is equal to f lambda. V and c are kind of interchangeable here, and they mean the speed of the wave, which is in meters per second. And I guess the c, the difference is c always refers to the speed of light. And so all of the different EMR that you're going to learn about this week from, well, we have radio waves and microwaves, infrared, ultraviolet, X-rays, and gamma rays. They're all waves, which means they're three-dimensional waves with properties such as frequency and wavelength. They're always going to be going the speed of light, though, which is a constant. And so there's our constant right there, 3.00 times 10 to the 8 meters per second. Frequency would refer to how many waves are going past one point in time per second. And so we call that just a hertz per second, 1 per second. And the last one we have, the last variable is the lambda, which is the Greek letter there, and that is going to be wavelength in meters. The first example I want to go over is going to be looking at the wavelength. And so, for example, here's a question right here. We have the question, this is from the textbook, and so the question states, determine the wavelength of this electromagnetic radiation. And we can see that it is 14 meters from this point to this point. And we now need to figure out how long one wavelength is. And so a wavelength is going to be measured as the same point to a same point. And so what I mean by that is we have up top here, we have our crests of the wave. Down here, we have the troughs of the wave. And so a wavelength is one wavelength will be will be from here, and then we would travel down this wave, and then we would go up to the exact same point right there. And so this would be one wavelength. Now take a look at our next wavelength. We go from here down, and then we go up to the exact same spot, and that would be another one wavelength. We then go from down here up and to the same spot again, and that would be one wavelength. You notice we're still not done yet, and so what we now need to do is take a look at that last little bit, and that last little bit is just going to be right there. So how would I describe that? Well, if you could imagine, this would just continue down. Trying to make that dotted, that didn't really work, but that would go back down and come back up like this. So how many wavelengths is that? Well, this is going, if you think about the sections, how many sections is broken down into, there would be one section here, one section here, one section here, and one section here. And so that would be a quarter wavelength, so 0.25 wavelengths. And so that means we would have a total of 1, 2, 3.25. This would be 3.25 wavelengths. Would be how many wavelengths this is equal to, and that is going to be equal to 14.0 meters. Now, once we have that information, we can then sort out how long the actual wavelength is. So we would take, this is just a simple elimination question, so we're going to divide by 3.25 on this side, and we're going to divide by 3.25 on this side, and lambda will equal 4.31 meters would be lambda in this case. There are a couple examples in your textbook, guys, I want you to try. Page 417, and that would be number 5. Okay, so page 417, number 5 would be a question. You can try those out on your own. The next question and last question of this video is going to be on the actual formula and how to use it. And so here's the question. The antenna of an FM radio station broadcasts electromagnetic radiation with a frequency of 104.5 megahertz. A driver in a car is receiving these FM radio waves while traveling down a highway at 90 kilometers per hour or 25 meters per second. So A, calculate the wavelength of the electromagnetic radiation. So A is calculating wavelength. So first of all, let's go through some of the knowns that we have here. We have a frequency, which is equal to 104.5 megahertz. Just like anything else in the metric system, and if you use page 1 of your data booklet there, you will realize that a mega is just a unit or a prefix we use in the metric system, and so this would equal 104.5 times 10 to the 6 hertz. The mega doesn't really help us right now, so we don't really want to use the mega at this point, and so that would be 104.5 hertz. And whether we want to keep it in hertz or per seconds, it doesn't really matter at this point. The other known that we know is that V is equal to C, which means this is going to equal 3.00 times 10 to the 8 meters per second. So we already have two variables in our formula, and it doesn't matter again what we use here. V is equal to, we could use V is equal to F lambda, or C is equal to F lambda, but we now know what we're solving for is lambda. Lambda is what we don't know, that is the wavelength. And so lambda will equal V over F if we divide by F on both sides, and this is going to be equal to 3.00 times 10 to the 8 meters per second, divided by the frequency, which is 104.5 times 10 to the 6, and that would be in per second. I'll show it as this time, just so that we can see we have a per second dividing by a per second, which means the per seconds cancel out, and we are left with 0.348 meters as our wavelength. In B, I like B. B is an interesting one because it shows us, maybe gives us a little bit more of a sense as to how vast our universe is. And I'll show you what I mean by that at the end of this question. So some of the FM radio waves can leave Earth's atmosphere and travel into space. Calculate how long it would take these radio waves to reach the moon, which is located about 3.84 times 10 to the 8 meters from Earth. Okay, so this formula, guys, is one that you've used since Science 10 at least, and probably in junior high a little bit as well. And we're just going to be saying, okay, well, first of all, we know D. D is equal to 3.84 times 10 to the, 8 meters. That's the distance from the Earth to the moon. We also know that this wave is traveling at the speed of light, which is 3.00 times 10 to the 8 meters per second. So the only thing we're missing here then is the time. How long will that take? And so we know our formula is going to be equal, is V is equal to D over T. V over T there, D over T. And that's going to be equal to, we need to solve for T here. So T is going to equal D over V, which is going to equal 3.84 times 10 to the 8 meters divided by 3.00 times 10 to the 8 meters per second. And we are left here with 1.28 seconds. Now, why is that important, or why is that interesting? I think it's interesting because that tells us that the moon is 1.3, if you will, 1.3 light seconds away from the Earth. And now we know in the vastness of the universe, we measure things in hundreds of light years, thousands of light years away, and now we know that we can compare that maybe a little bit now to light seconds away from the Earth, which is the moon, and it's 1.3. So, anyways, that's how you're going to use this formula, guys. Have a good week.